You have 500 containers running across 50 servers. One crashes at 3 a.m. Who restarts it? Who routes traffic away from the failed instance? Who spins up a replacement on a healthy server? Kubernetes does. Automatically. In milliseconds. No human intervention. No pager going off. Here's how it works. Today, we're breaking down Kubernetes from absolute zero. What it is, why it exists, how it works under the hood, and when you should or shouldn't use it. By the end of this video, you'll understand the full architecture, all the core concepts, and how companies like Google and Spotify use it to run millions of containers in production. Let's start with the problem that made Kubernetes necessary. Docker gave us containers. You package your application with all its dependencies, every library, every binary, every configuration file, into an isolated unit that runs identically everywhere. Development, staging, production. No more works on my machine problems. Containers are portable, lightweight, and fast to start. They share the host kernel, which makes them far more efficient than traditional virtual machines. But here is the fundamental limitation. Docker, by itself, runs containers on one machine, one single host. And in production, one machine is never, ever enough. Think about what production actually demands. You need multiple machines for redundancy. If one server dies, and hardware will eventually fail, your application must keep running on other servers. You need automatic restart. If a process crashes at 3 a.m. because of a memory leak, something must bring it back immediately without waking up an engineer. You need horizontal scaling. Traffic spikes 10x on launch day. You need more instances right now, not in an hour. And you need load balancing. Traffic distributed evenly so no single container gets overwhelmed while others sit idle. Managing all this manually doesn't scale. Imagine SSHing into 50 servers to deploy a new version. Imagine checking which server has spare capacity for another container. Imagine writing custom scripts to detect failures and restart processes across your fleet. Imagine doing a zero downtime deployment by hand across dozens of machines. This is the problem of container orchestration. You need a system that automates deployment, scaling, networking, and lifecycle management across many machines. And Kubernetes, abbreviated Kubernetes because there are 8 letters between K and S, is the industry's standard container orchestrator. It was created by Google, open-sourced in 2014, and manages containers at scale across multiple machines. It handles deployment, scaling, networking, and failure recovery, all automatically. Now let's look at the architecture. A Kubernetes cluster has 2 main parts. The control plane, which is the brain making decisions, and the worker nodes, which are the muscles actually running your containers. The control plane has 4 critical components. The API server is the front door to the entire cluster. Every single interaction with Kubernetes goes through it. Your kubectl commands, node status reports, scheduling decisions. Everything flows through the API server. It is the central communication hub. ECT is a distributed key-value store holding the entire cluster state. Every running pod, every created service, every configuration, all stored in ECT. Think of it as the cluster's database. If ECT dies without backups, you lose your cluster state. In production, it runs as a replicated cluster of 3 or 5 instances. The scheduler watches for newly created pods that don't have a node assigned. It evaluates which node is the best fit based on resource requirements, constraints, affinity rules, and available capacity. It makes the placement decision but doesn't run the pod itself. The controller manager runs multiple control loops. Each controller watches a specific resource type and ensures actual state matches desired state. You declare 3 replicas. The controller constantly checks. If one dies, it creates a new one. If there are 4, it terminates one. This is the reconciliation loop, the fundamental principle of Kubernetes. Now worker nodes. Each one runs 3 things. The kubelet is an agent on each node. It receives pod specifications from the control plane and ensures the described containers are running and healthy. It reports back regularly with status updates. If a container crashes, the kubelet restarts it according to the restart policy. Kubeproxy handles networking. It maintains routing rules using iptables or IPVS so traffic reaches the correct pods. It handles load balancing across pod replicas and enables communication both within and outside the cluster. The container runtime, typically containered, actually pulls images and runs containers. Kubernetes uses the container runtime interface to communicate with it. Docker used to be the default, but containered is now standard since Kubernetes 1.24. Now the key concepts you need to understand. A pod is the smallest deployable unit in Kubernetes. Not a container. A pod. It holds one or more containers sharing the same network namespace and storage volumes. They communicate via localhost. Most pods have a single container, but sidecar patterns use multiple containers for things like logging or proxying. A deployment manages pods declaratively. You specify how many replicas you want, which container image to use, resource limits, and how updates should roll out. The controller creates pods and ensures the right number are always running. Pod dies. New one appears immediately. You never create pods directly in production. A service provides a stable network endpoint. Here is the problem it solves. Pods are ephemeral. Every time a pod restarts, it gets a brand new IP address. You cannot hardcode pod IPs because they change constantly. A service gives you a permanent, stable address and DNS name. It load balances traffic across all matching healthy pods automatically. Pods come and go. The service stays. Namespaces provide logical isolation within a cluster. Development, staging, and production can share one physical cluster but live in separate namespaces. Each namespace can have its own resource quotas, access controls, and network policies. ConfigMaps and secrets externalize configuration from container images. Database connection strings go in ConfigMaps. Passwords and API tokens go in secrets. Mount them into pods at runtime as environment variables or files. Same container image across all environments. Only the config changes. Ingress handles external HTTP and HTTPS traffic. It provides host-based and path-based routing. Traffic to api.example.com routes to the API service. Traffic to web.example.com routes to the frontend. It handles TLS termination and can add rate limiting at the edge. Now scaling. One of Kubernetes' most powerful features. The horizontal pod autoscaler monitors metrics like CPU utilization and memory usage. When CPU crosses your threshold, say 70%, it automatically creates more pod replicas. When load drops, it removes extras. You set minimum, maximum, and target. Kubernetes evaluates every 15 seconds and adjusts automatically. The cluster autoscaler handles infrastructure-level scaling. When pods can't be scheduled because all nodes are at capacity, it talks to your cloud provider and provisions new VMs. When nodes are underutilized for an extended period, it drains their pods and terminates the machines. Fully automatic infrastructure scaling that saves money. Rolling updates deploy new versions with zero downtime. New pods come up with a new version. Health checks pass. Then old pods terminate gradually. At no point is your service completely down. If new pods fail their health checks repeatedly, Kubernetes halts the rollout and can automatically roll back to the previous working version. Zero downtime deployments with automatic failure detection and rollback. Self-healing runs at every level. Container process crashes. The kubelet detects it through liveness probes and restarts it. Entire node goes down. The node controller detects missing heartbeats, marks the node as not ready, and controllers reschedule all affected pods on a healthy nodes. Your application heals itself without anyone touching anything. Networking and storage. Every pod gets its own unique IP address. Pods communicate directly across nodes through a flat network created by CNI plugins like Calico, Flannel, or Cilium. No NAT between pods. Simple and predictable. Services provide stable DNS names. Create a service called MyDatabase in the production namespace. Any pod in the cluster reaches it at mydatabase.production.svc.cluster.local. This DNS entry updates automatically as pods change. Load balancing is built in at multiple levels. Cluster IP distributes traffic internally. Node port exposes on each node. Load balancer type integrates with cloud providers for external access with public IPs. Persistent volumes provide storage that survives pod lifecycle. Your database data persists even when pods restart, get deleted, or move to different nodes. The pod is just compute. Storage lives independently. Storage classes enable dynamic provisioning. You define what kind of storage you need in your pod spec. SSD, HDD, whatever performance tier. And Kubernetes automatically provisions it from your cloud provider when the pod is created. Real world at scale. Let's look at who actually uses Kubernetes in production and how they benefit. Google invented Kubernetes. It evolved from Borg, their internal system that had been managing containers for over 15 years before Kubernetes was open-sourced in 2014. Google launches over 4 billion containers per week across their infrastructure. Kubernetes is essentially the community version of what Google ran internally at massive scale for over a decade. Spotify runs 4 million containers across more than 2,000 microservices on Kubernetes. They migrated from custom tooling and saw massive improvements in developer velocity and resource efficiency. Airbnb moved from a monolithic application to Kubernetes microservices. This enabled hundreds of independent deployments per day with teams owning their services end-to-end. For learning, use Minikube or Kind. Both create full clusters on your laptop for free. No cloud account needed. For production, managed services handle the complexity. Amazon EKS, Google GKE, Azure AKS. They manage the control plane while you focus on your applications. But when should you not use Kubernetes? Simple apps with 1 to 3 containers? Docker Compose is more than enough. Single YAML file, one command. Your app runs on a single machine. No cluster needed. Small team without DevOps expertise. Managed platforms like Railway, Render, or Fly.io handle deployment automatically. Push code, get a running app. No YAML configuration. No cluster management. The overhead is real and significant. Steep learning curve. Complex networking. Mountains of YAML files. You need monitoring with Prometheus and Grafana. Centralized logging. Alerting infrastructure. RBAC security. Pod security policies. Resource quotas. Practical rule of thumb. If you have fewer than 10 services, you probably don't need Kubernetes. The operational complexity, the infrastructure cost, and the management overhead outweigh the benefits at that scale. Start with simpler tools like Docker Compose for local development and a managed platform for production. Adopt Kubernetes when you genuinely outgrow those simpler solutions and have the team size to support the operational requirements. Let's summarize everything we covered in this video. Kubernetes equals desired state plus reconciliation loop. You declare what you want in YAML manifests. 3 replicas, expose on port 80, autoscale between 3 and 10 based on CPU. Kubernetes controllers then continuously work to make reality match your declarations. It figures out how, where to place pods across available nodes, how to route traffic efficiently, when to scale up or down based on metrics, and what to do when failures inevitably happen. The core building blocks. Pods run containers. Deployments manage replicas and rolling updates. Services provide stable networking. Everything else in the Kubernetes ecosystem, from Ingress controllers to custom operators to service meshes, builds on top of these 3 fundamental primitives. If you found this helpful, the next video in this series covers CI/CD pipelines. How to automatically build, test, and deploy your code every single time you push changes to your repository. It's the natural next step after understanding orchestration. Subscribe so you don't miss it.